So as we look at the periodic table, we can see the trends in the atomic radii of the elements. So generally, as we go across the period, so we go from like lithium across to fluorine, we see that the size decreases. The atomic radii gets smaller. So in lithium, the atomic radii is about 152 picometers. And then as we go across, we see that fluorine is slightly less than half that. This is atomic, of course. This is not taking into account ionization or anything like that. But we see that going from group 7 to group 1A, we have an increase in size. We also see an increase in size as we go down the group. The increase in size as we go down the group is because we're adding electrons to successively higher quantum numbers. So n is 1, n is 2, n is 3, n is 4, and so on. Going from right to left, we have an increase in size because the effective nuclear charge of lithium is much less than that of the valence electrons is much less than that of fluorine. Fluorine, the electrons are held much tighter because every time we add an electron here, the distance of that electron from the nucleus is not increasing. Rather, it is just the strength of the attraction from the nucleus is increasing because it gets progressively more positive as more protons are added going from lithium across to fluorine. And the electrons are still at more or less the same distance or in the same shell anyway. And so they are not shielded by, like the inner electrons that shield lithium is the same number as shields fluorine. However, there's only 2 shielding electrons. And then these other outer electrons in the n is equal to 2 shell are pulled very tightly by this highly positive nucleus. So size goes up on going down a group because electrons are added further from the nucleus. There is less attraction. And size goes down on going across a period as the effective nuclear charge of the elements increases. So let's think about this. So just do a concept check 1 and 2. So which of the following atoms is the largest? In 1, is it going to be potassium, rubidium, sodium, or cesium? So have a little think about that, 5 or 10 seconds, then pause if you need more time. Okay, so the answer is going to be cesium. Why is it cesium? Well, cesium is the one that is closest to the bottom left of the periodic table, and so we can check that in a moment. Let's do number 2. Which of these is going to be the largest? Aluminium, chlorine, magnesium, or phosphorus? Answer soon. Okay, so these are all in the 3rd row of the periodic table, which means that by and large, the one closest to the lowest group is going to be the one which is largest. And so that's most likely to be magnesium in group 2A. Okay, so let's check and see if our answer is right. So let's check first potassium, rubidium, sodium, and cesium. So we had potassium here, we had sodium here, we had rubidium, cesium, all of which are in the same group 1A. So the one at the bottom, cesium, is going to be the largest. The other one was looking at chlorine, phosphorus, aluminium, and magnesium. So what I said was the one that was in the lowest group number, which would be magnesium in group 2A, would be the answer. And so that is indeed correct. You see chlorine is 99 picometers, phosphorus 115, aluminium 143, and magnesium 160. So magnesium is the largest, has the largest atomic radii of those elements. So ionization energy is the energy required to totally remove an electron from an atom. So the delta U is equal to the ionization energy, IE. So the minimum energy required to remove an electron from the ground state of a gaseous atom. ionization energy 1 is the energy needed to remove the first electron from a gaseous atom. So in the case of potassium plus ionization 1, so we're adding enough energy, we create potassium plus, so the cation, and then we also have a free electron. And so this energy here is delta E is equal to plus 419 kilojoules per mole. The plus sign here means that we need to give that energy to the system. So we need to provide energy from somewhere. I2 then, so the energy needed to remove the second electron from a gaseous plus 1 ion. So here we have K plus I2, so that's the energy going in here, plus K gives K2 plus plus an electron. And so here we have delta E is now equal to plus 3051 kilojoules per mole. It is a substantial increase. So you see, it's not linear well, it doesn't really appear to be linear in such, like it's not twice this. I mean, you might think that the first one is 419, so shouldn't the second one be twice this? Well, no, in fact, it becomes much more difficult typically to remove the second electron after the first. And you can think about that rationally in sort of a way that it says that, well, if I'm reducing an electron, maybe I'm increasing the effective nuclear charge in some way or changing it. So the attraction is much greater now than it was before. If we think about our periodic table, we have, as we decrease in size, we increase the ionization energy. So things like fluorine have a higher ionization energy than lithium. And that's because the effective nuclear charge changes. And so the electrons are held tighter in fluorine than they are in lithium. Again, we also have the same thing. As we go down the group, ionization energy increases as size increases, or decreases as size increases. So at the top here, around about lithium or whatever, we have smaller size, but higher ionization energy. So it's easier to ionize cesium compared to sodium. Removing more than one electron. So the general trend is that the first ionization energy is going to be less than the second. It's going to be less than the third. It's going to be less than the fourth. So the first, second, and third ionization energies for the main group elements of periods 2 and 4. So here we have lithium, beryllium, boron, carbon. You can see that there's a general trend that we're increasing the ionization energy as we go across the period. Now, it's not uniform. There are some exceptions, but we will talk about that in a moment. So here we have, notice the jump from I1 to I2 for beryllium is not as great as that for lithium. Why? So here we have beryllium goes to the second ionization energy, which is actually much less than lithium's. And that's because if we do the second ionization energy, so beryllium is in group 2, so group 2A, and lithium is in group 1A. So if we remove 2 electrons, so its outer configuration is going to be what? 1s2, 2s2 for beryllium. Beryllium. Okay, so 1s2, 2s, 2. If we remove 2 electrons, then we go to beryllium 2 plus. It now has only 1s2 electron configuration. And so that means that it now has a noble gas configuration, the same as helium. And we already talked about how the fact that noble gas configurations are generally very stable. So here we see the gain stability of a noble gas configuration, electron configuration. And so you can also see that with, for example, boron. So for example, here we have the jump from first, second ionization energy, but then from second to third is not as great as first to second. And then indeed, if you look here, this ionization energy from second to third for beryllium is massive, whereas for boron, it's quite manageable. And that's, again, because boron has a noble gas configuration if it loses 3 electrons. So it normally is what, 1s2, so boron, 1s2, 2s2, 2p1. And so if we lose 3 electrons, we end up with B3 plus, which now has the electron configuration of 1s2. So we've lost these and we've lost these. So we end up with a noble gas configuration the same as helium. And so that gives additional stability. So periodicity plot. So ionization 1 versus atomic energy creates some anomalies. So lithium, beryllium, and then we have a drop down to boron, and then we have carbon, nitrogen, then a drop to oxygen, fluorine, and nitrogen. And so the reason for this is, again, due to orbital filling. So if we think about going from, if we lose just one electron in beryllium, we're going from 2s2 to 2s1, so a half-filled orbital. So the fully filled orbital in this case was much more stable. So this energy here is going to be higher. Whereas the energy decrease is going to boron, because by doing the first ionization energy, what we're able to do is we're able to remove this electron. So we lose a half-filled orbital, and we now have a fully filled orbital, the 2s2, as our valence orbital. And so that's actually more stable. Then in the case of, for example, nitrogen to oxygen. So nitrogen here has 2s2 and 2p3. So that would mean that it has 3 half-filled orbitals. And so that's actually a nicer configuration than the oxygen, which would have non-sort of symmetry in its orbitals. So there is some energy gain, or sorry, some stabilization gain whenever we remove an electron to create a system which has all half-filled orbitals. And so that's why there's a decrease in energy as we go from nitrogen to oxygen. So this is a preferred configuration compared to this. Because there's in a lot of this, there's kind of like this symmetry element. So having everything the same is generally going to be more stable than having differences. So like you can see, this is fully filled and then half and then half. Generally, nature prefers for everything to be more or less the same. So like this, there's some stability gain there. Okay, so concept check then. So concept check 1. We're going to be thinking about which of the following atoms has the largest value of I1. Is it going to be potassium? Is it going to be rubidium? Is it going to be sodium? Or is it going to be cesium? So these are similar questions that we had earlier. Think about the trends that we mentioned. So 5 or 10 seconds, think about it if you need more time. Pause if you need more time. Okay, so for the first one here, these are all in group 1A. So they all have one electron. So the electron configuration is going to go from the 1A to the nearest noble gas configuration. So they're all going to be stabler or more, so they're all going to have like a stability associated with their 1+ ion. So that's not going to be a problem. So then the only thing we have to think about now is if they're all in the same group, 1A, then which one of them is going to have the highest ionization energy? Usually that's the one that's the smallest. And so the one that's the smallest here is going to be sodium. And so it's going to be the one with the highest ionization energy because its electrons are held closest to the nucleus, and so they're hardest to remove. Then in concept check number 2, think about this. So we have which of the following has the largest value of I1? So is it going to be aluminium, chlorine, magnesium, or phosphorus? So this is a similar situation as we had before. We're going across the period. Have a little think, 5 or 10 seconds. Pause if you need more time. Okay, so, I just realized, okay, we need to go back to question 1. I realized I did the wrong way around. Oh, no, I didn't. No, I didn't. Not so question 2. We're thinking about the largest value of I1, so it's going to be the one that's furthest to the right. So, because these are all in the second period. This is going to be the one that has the most electrons in its valence, so it's going to be chlorine. Chlorine actually wants to gain an electron. It doesn't really want to lose an electron. Then in the third one, now we've got a question which is a little bit trickier. You know, we're dealing with going across the period. We're dealing with different groups. We're going up and down. So 5 or 10 seconds, pause if you need more time. Which of the following will have the largest value of I1? Pause if you need more time. Okay, so let's have a look at which groups each one of these is in. So K is in group A1, magnesium is in group 2A, rubidium is in group 1A, and calcium is in group 2A. So generally, our ionization energy is largest as we go left to right. It's an increase going left to right. Also, increases going up the period. So this is higher. So higher energies in this part compared to this part, and then higher energies here compared to here. Okay. So that means that potassium and calcium are in the same row. So calcium would have higher ionization energy than potassium, but magnesium is above calcium, so it's going to be magnesium. Magnesium is higher than any of these, so it's closer. It's got the lowest principal quantum number for its valence electrons, and it's also the one that's in the highest group number. So it's 2A. So this is going to be the one with the largest value of I1. Ionization energies then. So as we see, they increase as we successively remove electrons. Here we have for magnesium. You can see that in sodium, there's a stark increase after the first ionization energy, whereas for magnesium, the first and second are not that hard, and it's the third ionization energy which is harder. Aluminium, you can see that the first three are okay, and then it's the fourth one. This is because aluminium is in group 3A, so it can go pretty easily to lose electrons to go across to, what's it going to be, neon? Yeah, I think it's neon, noble gas configuration. So then if we can think about which group is this element X going to be in. So we can see that the first, second, third, fourth electrons are easy to remove, but then the fifth and the sixth are hard to remove. So it means that these 4 electrons are probably in the same shell, and is probably going to be the same for the first to fourth, and then it's going to be changing for the fifth and the sixth. So it's going to be a lower shell potentially. So if there's 4 electrons there, that probably means it's in group 4A, could be something like carbon. Here we have the group. What group is element Y in? So I'll give you 5 or 10 seconds. I think you can do this after you've seen the example I just did. Pause if you need more time. Answers coming soon. Okay, so here again, we've got a similar system. So 1 to 6, ionization energies 1 to 6 are all going to be in the same value of N. So we remove the first 6 electrons, okay, and then it's the 7th and 8th electrons, which are presumably in a different value of N. Then we have 6 in the same value of N, so 6 in the same shell, which probably means we're in group 6A, so something like oxygen, maybe oxygen. So okay, so we'll have here a bunch of ionization energies. We have to identify the group that elements X, Y, and Z are in. So here's the first, second, third, fourth, fifth, and sixth ionization energies. So we've got element X, we've got element Y, and we've got element Z. So we'll do X first. You can do all of them if you want in one go. I'll go through them one by one. So pause if you need more time. We'll do element X first. Pause if you need more time. Okay, so the idea here is, again, very similar to the graphs that we just looked at, and we're trying to see where the biggest jump in energies is. So 700 to 1500, that's this is times 2, more or less. We just do it roughly. And then here to here, this is going to be what? About times 5, something like that. And then here we have less, like times 1.5. So it seems like the biggest jump is going to be here between these two. This happens after 2, 1, 2 ionizations. So most likely it's going to be group 2A. Then we'll do Y next. So again, 5 or 10 seconds. A few more time, just pause. Pause if you need more time. Answer coming soon. Okay, so we do the similar thing as before. So here we have it's by times 2. Here we have again by times 2. Times 1.5. Then this is times 4 or thereabouts. And then times, what's that, about 1.2. So it seems to be that the biggest jump is between here and here. So that means we have like these electrons are in the same shell. So that's 1, 2, 3, 4. So it's most likely going to be group 4A. Then we'll do another one. The last one is Z. Take 5 or 10 seconds to check out the answer that you think might be yours. And then we'll go through it. Pause if you need more time. Pause if you need more time. Okay, so let's go through it. We'll do the same thing again. So it's about times 2 or thereabouts, slightly less than times 2. Here we have again slightly less than times 2. Here again, slightly less than times 2. Times 2. Turns out they're all, so there's just a slight jump here. That's about times 1.5. Or well, not really. And then this is times 1.1, 1.4. So not really any noticeable jumps. So we have how many electrons here? 1, 2, 3, 4, 5, 6, 7. Most likely it's in group 7A. There's no significant sort of jump. There's nothing here you Okay, so the next thing that we need to talk about is electron affinities. We are adding an electron rather than taking one away. So electron affinity, otherwise known as EA. So here the energy change for the process of adding an electron to a neutral atom in the gaseous state to form a negative ion. So this is where we're going the other way and adding electrons. So for example, chlorine in the gas form, so this is monoatomic chlorine. We add an electron and then this forms the chloride anion. So there is a negative change in energy here because this is a favorable process. And so this is an exothermic process. Energy is being released. So chlorine likes to get an extra electron. And we'll see this and the reason for this as we go through. So remember the sign, the negative sign here for the energy means the process is favorable, and the trend increases as you go from left to right and go from the bottom to the top. So that means like things like fluorine, which had the sort of highest ionization energies, will now have the best electron affinities. So they don't really want to be ionized. They much prefer to be have an electron added. So here we have the electron affinities of the different halogens. So this is group 7A. So fluorine here has a very favorable energetic process to gain an electron. It increases slightly for chlorine and then decreases as we go down the group to bromine and iodine. So some elements like the noble gases do not have electron affinity values. They have no affinity for electrons because they have a full valence. So Br2, so bromine plus iodide gives iodine plus bromide. So which will this reaction proceed? We need to be thinking about the sort of energy differences. We need to think that which one prefers to have the electron. So right now, iodine, or iodide in this case, has an extra electron, which it really wants to have. But does bromine want that electron more? And the answer is yes, it's got this higher electron affinity. So the energy is going to be lower for the bromine and bromide. And so we're going to end up with a transfer of the electrons. So this reaction will proceed. So ionization energy versus electron affinity. So ionization energy measures the ease of losing an electron and is always endothermic. EA measures the ease of gaining electron and is often exothermic, but not always. So exothermic means it gives out heat. It means it's a favorable process. Endothermic means that some energy needs to be put into the system for it to affect this change. So the group trends for the active metals. So for example, in group 1A, the alkali metals is their name. And we have here the different, so lithium, sodium, potassium. So that's going down the group. So lithium's at the top, then sodium, and then potassium. And so this is their reaction with water, and they all undergo fairly similar reactions. Lithium, if you put some water on lithium, like here we have a pipette that comes in and drops a little bit of water on lithium, we can see that it reacts quite violently. It gives off hydrogen gas, starts to bubble and foam. The reaction gets more extreme as we go down the group. So sodium also reacts with water, but in this case, it's not kind of dangerous to come in with a pipette, and so or a dropper, and it's now we need to set up the system so that it drops very gently, and you can see that even just one drop of water is going to create a violent reaction. And this reaction gets more violent as we go down the group, as the metal becomes more reactive. So the halogens then here are some of their properties, and what we're interested in here is their ionization energies, which decrease down the group. So it's easier to ionize iodine than it is to fluorine, and that's kind of the same trend that we have for lithium, sodium, and potassium. It's easier to ionize potassium than it is to sodium, than it is to lithium. Here we have the densities change, so it gets denser as we go down. The melting point changes. So for example, iodine is a solid at room temperature. The rest are gases, although bromine, you can cool it down and it can become a liquid. Sizes change as well, as we add electrons to ever increasing n values, we get larger and larger atoms. And then this is their electron configuration in their valence electron configuration. So you can see here 2s2, 2p5. So it's n is equal to 2 for the valence, n is equal to 3 here for the valence, n is equal to 4 for bromine, and n is equal to 5 for iodine. So the halogens are very interesting. They're highly reactive. There's lots of chemistry known about them. So group 7a, the halogens. So the chemistry of the halogens is dominated by gaining an electron to form an anion. So we have X2, where X is the halogen. Could be chlorine, could be fluorine, could be bromine, could be iodine as well. So for example, we have chlorine, Cl2, plus 2 electrons, gives us 2 chloride anions. Okay. So fluorine is one of the most reactive substances known. Here, the fluorine reacts quite easily with water to form HF, which is dissolved in water. This is what this AQ for aqueous stands for. So it means it's dissolved in the water. So it's in the water. That should be a 2. Okay. So it's in the water. Then we have oxygen gas given off, and this oxygen gas is obviously quite flammable. But you can see this here, the energy is what? It is negative, meaning that this is a favorable process. It means it happens quite easily. So all halogens consist of diatomic molecules X2. So this is their elemental form is X2. So F2 or Cl2 that we saw up here, or Br2, and so on. So they also react, in this case, with phosphorus, quite violently, you can see. So here we have chlorine reacting with phosphorus to give PCl3. So we learned about that in the first module. We did a problem on chlorine reacting with phosphorus, if we recall. And you can see the reaction is pretty violent. So we're just adding chlorine gas to the phosphorus solid here, and then you can see this flames as the reaction happens and the electron transfer happens. So here we have bromine with phosphorus as well, so that's also highly reactive. And then here we're doing iodine with zinc, because iodine with phosphorus is not an appropriate demonstration. And so you can see here we've got this smoking reaction here as iodine gas is given off. That's this purple color. So alkali metals then, so this is group 1. So 2M is the metal, plus water react to give 2MOH plus hydrogen gas. So note the trend in reactivity. So the reactivity increases as you go down the group. Is this what is expected from the trend in ionization energy? So does the ionization energy give us any sort of indication that this is what is going to happen? By and large, it does, because the ionization energy, if we recall, goes down. So as we go down the group, the ionization energy decreases. So ionization energy decreases as we go down the group. So that means that it's going to be easier to affect this change, where we have to lose an electron. So the electron is easier to remove for example, cesium than it is for lithium or sodium. So the reaction is going to proceed faster, be more violent, give out more energy for cesium than it is for lithium. So rank the following ions in order of decreasing size. So here we have sodium, we have nitride, we have magnesium 2+, we have fluoride minus, and oxide 2-. Here we have their symbol. Here we have the number of protons. Here we have the number of electrons. They all have 10 electrons. And here we have the ratio of the electrons to protons. Let's rank them in size, going from decreasing size, so largest to smallest. So which one is going to be the largest? Put that first, and then which one is going to be the smallest? Put that last, and then that order 1 to 5. So again, give you 5 or 10 seconds. Pause if you need more time, and then we'll go through it. Pause if you need more time. Okay, so what we're looking for here is the largest one. So usually the size increases. So remember the size earlier we learned about in atomic size, it was driven by what? It was driven by the effective nuclear charge. So previously things like fluorine were smaller than sodium because the fluorine electrons in the valence were held much tighter than the sodium ions or sodium electrons were. But what happens if we have now added an electron? We're now increasing the number of electrons, and so we're decreasing the effective nuclear charge that each one feels. And so what happens is that things like fluorine get a little bit bigger, F minus get a little bit bigger. Oxide, O2 minus, also gets a little bit bigger. Nitride electrons in the valence. And then we also have, in case of magnesium, of electrons, we've removed the electrons have been removed. So the 3s electrons have been removed here. So now we're down to the valence electrons being in the n is equal to 2 shell. And at that point, those electrons are being held much, much closer to the nucleus because they're experiencing now no longer shielded by as many electrons. There are now fewer electrons than there are protons, and so the attractive force of these protons on these electrons is now greater. So what happens is that cations contract in size, whereas anions, the negatively charged ions, they expand. And so that can also be seen in this ratio of electrons to protons. And generally, we could say that since these are all in the same so these ions here would be most likely going to be larger than the cations. So we would probably have magnesium 2 plus as being the smallest, then sodium plus being the next smallest, and then we'd look at the anions and determine which one is going to be the largest and which one is going to be the smallest here. So most likely, if we follow this ratio of electrons to protons, we're going to probably be looking at nitride as being the largest, and then oxide, and then fluoride. So it goes sort of like N3 minus, O2 minus, and F minus. And so here we can see the working that we've got. So what they've said here is the answer is, since N3 minus nitride has the highest ratio of electrons to protons, it must have the largest radius. Since magnesium 2 plus has the lowest, it must have the smallest radius. The rest can be ranked by the ratio. So here's the ratios. So largest, smallest. This is the second largest, third largest, fourth largest, smallest. And so we rank them like this, so decreasing size. So nitride is the largest, magnesium is the smallest, the rest go in between. And notice that they all have 10 electrons. They are isoelectronic, same configuration as neon. So moving through the periodic table, if we go for atomic radii, as we go down a group, we increase the size, and as we go across the period, we decrease the size. This is due to the effective nuclear charge. Ionization energies, they decrease down a group and increase across the period. Again, this is all to do with reaching a noble gas configuration and also the effective nuclear charge. And then electron affinity, as we go down a group, it becomes less exothermic, and as we go across a period, it becomes more exothermic. Okay, so let's move on to the next